Hello, SSN viewers! For over a century, chemists have been building their understanding of how atoms form bonds. We've grown used to thinking of chemical bonds as sharing two electrons, the bread and butter of covalent chemistry. But what if a bond could form with only one electron? It sounds unconventional and perhaps even unstable. Yet, that's precisely what a recent breakthrough in the journal, Nature has demonstrated, the existence of a stable carbon-carbon one-electron sigma bond. Let's dive into how this unique bond comes into being. In a standard covalent bond, two atoms share a pair of electrons, which helps hold them together. In contrast, a one-electron bond involves just a single electron shared between two atoms. This creates a different kind of attraction. While less stable than a traditional two-electron bond, it's still strong enough to hold the atoms together, albeit with less energy. The single electron forms a half bond, providing a lower bond strength than a typical covalent bond but still enough to stabilize certain molecular structures. In the case of this study, the researchers from Hokkaido University, Japan managed to stabilize a one-electron bond between two carbon atoms by crafting a specially designed molecular system. They used a rigid molecular scaffold that constrained the geometry of the molecule, effectively forcing the two carbon atoms into close proximity. Additionally, large substituents were placed near the bonding site to shield the delicate bond from reactive external influences. This combination of structural constraints and protective groups allowed the one-electron bond to persist under conditions where it would typically react or degrade. To confirm the existence of the one-electron sigma bond, the research team employed a multifaceted approach, X-ray crystallography. This powerful technique revealed the precise arrangement of the atoms, including the distance between the carbon atoms, which indicated the presence of a bond. Electron paramagnetic resonance (EPR) spectroscopy. EPR is especially sensitive to unpaired electrons, making it the ideal method to detect the single electron responsible for the bond. The EPR spectrum provided clear evidence that an unpaired electron was shared between the two carbon atoms. Computational chemistry, advanced theoretical calculations supported the experimental data, showing that the molecular orbitals involved were consistent with a one-electron bond. These calculations also helped to explain the stability of the bond by revealing how the electronic structure was influenced by the rigid framework and protective substituents. This finding doesn't just challenge our understanding of bonding, it expands it. The existence of a stable one-electron carbon-carbon bond opens new doors in chemistry. It could lead to innovative ways to design molecular materials that exploit the unique properties of one-electron bonds, such as unusual magnetic or electronic characteristics. Potential applications might include novel materials for electronic devices, molecular switches, or even quantum computing components, where the behavior of single electrons can be crucial. In essence, what this study shows is that even the most fundamental concepts in chemistry, like how atoms bind together, can still surprise us. The discovery of a stable carbon-carbon one-electron bond isn't just a rare molecular curiosity, it's a reminder of the untapped potential and complexity still hidden in the atomic world. As researchers continue to explore these unconventional bonding patterns, who knows what other surprises lie ahead? For a deeper dive into the study, you can check out the original article published in Nature, the link of which is provided in the description of this video.